Hey folks, we're continuing our lecture 2-4 here, finishing up chapter 2. This is part 3. We were looking at the penetrating power of alpha particles, beta particles, X-rays, and gamma rays, and I want to talk about those 4 types of radiation. So alpha particles or alpha radiation and beta radiation have some differences. They're both particles, but alpha particles are high energy. They're large and slow moving, and so they're not very good at penetrating. They have little penetrating power. They can be stopped by a piece of paper. But they are extremely dangerous if ingested or inhaled. So obviously inside the body, bad. Outside the body, can't really get in because they don't have the penetrating power. However, beta particle radiation can penetrate skin and so can cause damage due to the greater penetrating ability. They do actually have less energy than alpha particles, and they're much lighter than alpha particles, but they can penetrate through much more. X-rays and gamma rays both have less energy than alpha and beta particles, but far more penetrating power. So they are potentially far more damaging. However, there's a flip side, right? They have many medical applications because of their penetrating power. Can pass through your whole body, right? X-rays are used for imaging. They have different absorption, whether it's bones, muscles, or other material. And so what we get is based on how it's absorbed and transmitted through your body. You can see the bones inside, which is pretty amazing. And gamma rays have such penetrating power and high energy that they can actually be used almost like a knife for surgical reasons. So many beneficial medical applications. We just need to be careful with these types of radiation. So the core concept from all this is that the biological effects of radiation depend on its energy and on its penetrating power, which is the ability to pass through matter. Penetrating power increases from alpha particles to beta particles to X-rays to gamma rays. And it says here that energy increases in the opposite direction, but actually gamma rays have higher energy than X-rays. Otherwise, yes. Okay, so we do talk about biological effects and exposure. So radiation sickness is what's caused by exposure to radiation, and it can be acute, as in a single exposure, or chronic, as in small doses over and over and over again, every day, small doses. But radiation sickness results specifically from acute exposure to radiation. Radiation that you're exposed to has to be measured some way. And there's one way, which is to measure the amount of energy absorbed. So that's the absorbed dose, and the unit is the gray, or GY. However, the effective dose represents the biological damage. That's not just energy, but also takes into account penetrating power. So the gray is useful, but the sievert, the effective dose, is probably a better measurement because it's basically energy and penetrating power combined. And we're all exposed to some background radiation just in our everyday life. The natural background radiation, to give you some baseline, is approximately 24 millisieverts per year. So if we did a quick conversion, there are 1,000 millisieverts per sievert. And so we're all exposed on average, the natural background, about 0.024 sievert per year. Bergen was 0.024 per year, though. Okay. So this table shows acute radiation sickness. So that's exposure basically all at once. So 0.024 spread out over a year is essentially harmless. There's no symptoms. If you even got all of that at once, it's still not bad. Okay, but once we start getting up to 0.2 or 1 or more, you can have some very serious symptoms. And this term LD is loss of death. And so the number, this would be 10% of people exposed to that would die. So if you were exposed to an effective dose of 1 to 2 sieverts, there's a 10% chance of death from that. 6 to 10 we see is 100% death. So that's just that a body cannot survive that kind of exposure. So when it says that, for example, 2 to 3 sieverts has an LD of LD35, this means that 35% of the population exposed to that level of radiation will die within 30 days. So you might be wondering, like, what kind of effective radiation dose do we get, if we go and get an X-ray, right? So I wanted to show you this just so you're not too concerned in a general case here. So this is from a website, Radiology Info, which I have at the bottom. And here are some approximate comparisons of background radiation and the effective radiation dose in adults for some different procedures. And this is taking 3 millisieverts per year as the effective background. And we see that, for example, a CT scan of your abdomen and pelvis would give approximately 10 millisieverts, which is, 3 years worth of natural background radiation. So that's actually quite a bit, right? All of these abdominal procedures with CT scans give quite a bit. Computed tomography, which is actually just multiple X-rays in the abdomen and pelvis repeated with and without contrast, doubles it, right? And so that's about 7 years worth of background radiation. So that's quite a bit. If you go out for a spine X-ray, 1.5 millisieverts, just 6 months worth. But simply checking to see if you broke your toe, did you break your finger, extremity X-rays are about 3 hours worth of natural background radiation. That's probably not too big of a deal. Continuing here with some CT scans of different parts of your central nervous system are in the order of millisieverts, so close to about a year's worth of natural background radiation. I will point out, though, that even these numbers are not on this scale, right? Because 1 millisievert is 0.001 sievert, right? And so 10 is 0.01, and you'd have to have 100 millisievert before you start to get to, even close to this scale. So I wanted to add this information to that table so you know what we're dealing with. Most of these are going to add a few hours to weeks. A few here are years. And so those are ones that definitely want to be careful with and not do unless absolutely needed. X-rays are one way of imaging, but really there's lots of ways because the whole spectrum, it's all just light, but with different wavelengths, right? So it's absorbed differently, and we have different kinds of detectors. So I thought this was kind of cool, showing a hand with different types of imaging. All right, so that wraps up chapter 2. So I encourage you to go check out page 74 for a summary of the chapter. It has a list of all the core concepts from the sections. So this summary is a good learning tool, right? You can use it to assess your knowledge. Do you understand these core concepts? Do you think you understand them? Go through the list and also go to sapling and learning curve. And your textbook has questions. So it has practice exercises and alongside worked exercises in the text. And then at the end is a whole lot of additional exercises as well as keywords. Okay, so this wraps up chapter 2. Good job.